so I don't forget what to do. So I probably won't do them all today, but then there's also Thursday. Tomorrow's a holiday. So the first one says calculus exercise, and then after that it's a bunch of people's names, so people who did something important in the history get their name forever attached to the story. So we'll work my way down. And the last one, as you can see, sounds like it has nothing to do with geometry, it's gas dynamics. So that's the get there. Okay, that one you don't find in any books. It was my idea, but it's in the research paper. Okay, so I like it. Okay, so first let's do the calculus exercise, if I can do it correctly. So we make x, y, z, and now we take a, of course I can do spherical coordinates, so theta, phi, okay, and r. So spherical coordinates. And now let's take a sphere of radius a. So that's a sphere of radius a. Okay. And we take a circle going around the z-axis. Okay, and then this comes out with some angle, and we'll call that angle phi1. So if you want to think about it, you can go do the experiment. So this would be the ice cream cone. And then this where the ice cream would set, but it's not a very good, you didn't get a good deal, because the ice cream doesn't come up very high, it just comes up to the level of the sphere. So it wasn't a good deal. You probably, but anyway, so you get something here, and I'll draw the picture. So this part that you see, okay, in the, for the Earth, it would be the polar ice cap upstairs, or if it was down in the South Pole, it would be the Antarctic ice cap. So this is called the spherical cap. Okay, and that has an area. So the area of the spherical cap we can call A. And now the calculus exercise is what's A? Okay, well, the increment of area is A squared sine phi d theta on the sphere. So we have to integrate phi between 0 and phi1 and theta between 0 and 2 pi. So that's the area. Because that's just the integral of it. And that's easy to compute. And we get that the area A is 2 pi A squared 1 minus cosine phi1. Okay. But we'll rewrite this slightly and call R the intrinsic radius. By definition, is just A times phi1. Okay, now let's do a power series expansion. So everybody remembers cosine phi1 is 1 minus phi1 squared over 2 factorial plus phi1 over 4 factorial. Huh? So if I plug that into the formula, I get 2 pi a squared, 1 minus cosine, but 1 minus cosine is the first term is, right, 1 minus cosine, let's just write the first term. So I move this to the left-hand side, that means to the right-hand side, the first term is phi1 squared, and the next one is minus phi1 fourth over 4 factorial, etc. Okay, so I can use the eraser. What happened to the eraser? So let's plug that in. So it's phi1 squared over 2 factorial, and then phi1 fourth over 4 factorial, etc. Okay, well, first of all, what's the... so phi1 is r over a, right? In terms of this intrinsic radius. So let's rewrite this. Instead of working it in terms of phi1, let's write it in terms of r over a. So if I do that, what's the first term in the series? Okay. It's 2 pi divided by 2, which is nice. And then, so the 2's cancel. And then what's the next one? It's, I have that right? Some, looks okay. 2 a squared, 1 over, looks okay. So the first term in the series is 2 pi, that's right. So let's do this. So it's a squared, and then phi1 squared, which is, and phi1 is r squared over a squared. And then the next one is phi1 fourth, that's right. Phi1 fourth is r fourth over a fourth, 4 factorial. Okay, no mistakes. So far, so good? So let's just look at the first 2 terms. The a squares here cancel. The 2's cancel. Okay. Okay. Here the a squared hits the a to the 4th and becomes 1 over a squared. So far, so good? So let's write out the area formula, because now we're finished. You just have to interpret. So the area of the polar cap, this 2 pi was in front, right? The 2 factorial cancel this. Did I do the cancellation right? Let's just check what the right term is. So there should have been 4 factorial, which is 4 times 3 times 2. When it multiplies 2, it's 12. So whatever the next term is, so it's pi r squared, and then the next one is r to the 4th over 12 with an a squared downstairs. Okay, so the area of the polar cap is, to leading order, is those first 2 terms. But what was the Gauss curvature of the sphere? Well, remember, it's just 2 circles. The regular curvature of each circle was 1 over a, so the Gauss curvature of the sphere was 1 over a squared, so we'll call that. Okay. So we see the area of the cap is k r to the 4th divided by 12, and I think I need a pi. So far, so good? Okay, so that means if I differentiate a with respect to r squared once, what do I get? Pi, and then becomes minus pi over 6, because it's r squared squared times k r squared, huh? If I differentiate twice, dr squared twice, second derivative with respect to r squared, then I just get minus pi over 6 times k. So what's the point? The point is, how do we teach students the first year calculus about curvature? We say it's really the second derivative. Okay. Then so that's very good for curves in the plane. Okay, it wasn't very hard. We teach the students how to find the curve of a line in the plane. Okay, a planar curve, and we say it's really the second derivative. And if you remember to put in the square root of 1 plus f prime squared to the 3 halves in the denominator, you get 100 on the exam. If you forget, you get 99. Okay, the denominator isn't important. Okay, but now we introduce the concept of Gauss curvature, and to do Gauss curvature, it seemed, okay, we had to take Hessians and then determinants and stuff. So it wasn't derivatives, just normal everyday derivatives. It was cross partials, partial derivatives. But we see, in fact, we can think of the Gauss curvature as a derivative. It is a second derivative, but it's the second derivative of what? And there are many ways to think about it, but this calculus exercise tells us one way to think of the Gauss curvature is just multiply through. So this would be, I can use the eraser. Okay, I'll just write it. So what does it say? It says the Gauss curvature is 6 divided by pi times minus 2, the second derivative of the area of the spherical cap, so minus 6 over pi times the second derivative of the area of the spherical cap. So there is a way to calculate Gauss curvature, among other ways, from ordinary derivatives, and that's the point of the exercise. So if you want to know, if you were here, okay, and you can fit a sphere, okay, you don't have to find the, okay, I should say, if you can fit a spherical cap and see how a spherical cap moves, then we have with respect to its intrinsic radius r, then we can compute the Gauss curvature. So it's an exercise that says, okay, in fact, Gauss curvature is a second derivative, but a second derivative of what? And it's a second derivative of the spherical radius of the spherical cap. Okay, so I did the calculus exercise. So now let's do the next one, is Fresnel's array, and this gets more important. So this is usually in most calculus books. It's in the one they used at Wisconsin, the Fresnel's array. It's in there in sometime in the middle of the book. It's there when they introduce the tangents, normals, and binormals, and it's in all the books. But of course at Wisconsin, they never did it as an exercise. It's too hard for the students. Okay, so, but of course for us it's not hard at all. So ironically, of course, in the course they would leave out the most interesting stuff. So let's do that. If I can remember. So let's take x, y, z if you want. Doesn't make it. Instead of a curve in the plane, we'll do a curve in space. So like the trajectory of the chalk. Here's a curve in space. So it has points, and let's parameterize it by t. So we'll use this usual notation. So a vector going out to a point on the curve I'll call x of t. Okay, so we know how to compute a tangent. We've done that before. So t of t, well, it's not quite the tangent. I have to normalize it. So I have to take this one. So x dot t and normalize it. So let's use the velocity vector and then normalize it. So I get t of t. So now I have the unit tangent. So t of t is v dot, I'll call dot for derivative, over v of t. V over t. Okay. So this is v of t. The way we started the course. Okay, but we know it's the unit tangent, so t of t dotted with itself is 1. So if I differentiate that, I get the normal. So I get t dot of t dot t of t, reviewing, equals 0. So what's the unit normal? I'll use lowercase n. Even though I should use uppercase n, but there's a reason. The region is because in the second fundamental form, Gauss's notation was Lm and n. So I don't want to use the letter n for two different things. So I use lowercase n. So lowercase n is then t dot t and then normalized. And finally, if I take the tangent, so this was now the tangent, and then I found the normal. I don't know. Which way do you want to make the normal? Like that way? I don't know. I have no idea. Okay. So now if I take the tangent and take the cross product with the normal, I get a third vector, which is the binormal, b of t. And I have to make it a unit vector. So now I have three different vectors. I have the tangent, the normal, and the binormal. So that forms a local, I don't know, orthogonal coordinate system that's moving along the curve. Okay, now it's the exercise which we give to the students, but let's do the first part we already did. What's the time derivative, or the t derivative of the tangent? I did that the first day. So the time derivative of this tangent, that's it's in the normal direction. We just did that. Okay, that part I did. So the derivative of the tangent, of course, is in the normal direction, and the constant of proportionality, or the function of proportionality, might change. This is what we call the curvature. Okay, so that's the first one. Then now an exercise is, what are the other two? So what's the n dt and dv dt? Okay, so if you differentiate the n dt, it has to be, of course, can't be in the n direction because it's perpendicular to the n direction, so it has to be a linear combination of the other two directions, and tau of t. And the b dt is, I have to see the minus tau of t. That's lowercase n.
Is it arc length?
It could be arc length, any parametrization, but arc length, let's use arc length, yeah. This is good. Then it's for sure the old, so if t is arc length. then for sure it's that way we define the curvature. Okay, so then we have these three formulas, and then so this is the Fresnel equation. So what's new here is this is old. So, but when we differentiated the normal, which we hadn't bothered to do before, okay, we get something in the direction of the binormal, and we call that B. On the other hand, when we differentiate the binormal, we just get something in the direction of the tangent, because the binormal is both orthogonal to the itself. The time derivative of the binormal, since it's a unit vector, is orthogonal to itself. Okay, and it was constructed to be orthogonal to the tangent, right? Binormal. It's orthogonal, so it has to be just in the time derivative is just in the normal direction. Okay, so this was the curvature. And so tau of t has a name, is the torsion. So what's the point here? So why am I doing this? But this is a system of ordinary differential equations, in fact linear. So t is a vector, so this is three equations here, three equations here, three equations here. So it's 9 equations and 9 unknowns. So in fact, linear equations. Not autonomous, but that's okay. That means, since it's a linear equations, if the kappa tau are continuous functions of the independent variable t, then the existence uniqueness theorem for ODE says what? You give me two functions, the curvature and the torsion, and an initial position. Okay, an initial t is 0, n of t is 0, b of t is 0. Right? Then these guys are determined forever. So if you tell me the initial tangent normal binormal, okay, the way the thing is set up initially, and the torsion and the curvature, I know how this frame moves forever. So this is the Gauss frame. So we know the location. P of t, n of t, b of t forever. Right? As long as you give me this stuff. Okay? If you don't give it to me for all t, then I know it for small t. Okay, but then if I know t of t forever, then dx dt is known. So just integrate. Since if I know t of t, then x of t is just whatever its initial position was equals the integral from t0 to t of t of s ds. So then we know x of t forever. So it's a very nice result. Okay? If you give me two pieces of information, okay, do we know everything? And the answer is yes. So that's the Fresnel formula. Is there equivalent of the Fresnel formula for surfaces? This was curves. What's the equivalent of Fresnel for surfaces? So this was Fresnel is about curves. in R3. So how about surfaces in R3? So see, each one is a generalization. So we have to do the same thing for surfaces. And then we ask the same question. Are there a couple of functions that if I know something about a surface, say along a line, that I know something forever? So we ask the same question that we asked for curves, we ask for surfaces. So I erase and we do the same computation for surfaces. So let's erase it. So this was how tangents change and how normals change. So I have to write how tangents change and how normals change. Okay, but now it'll have partial derivatives because we're dealing with surfaces. Erase over. So let me get formulas, and I have it here. So let's draw a surface. And I'll use the letters U1 and U2 for my local coordinates, so there's the surface. Okay, so the surface, a point on the surface, we'll use our usual, so x, which is a function of u1 and u2, that'll be x1 of u1, u2, x2 of u1, u2, x3 of u1, u2. Now, of course, in this picture, it would be u1, u2, and x3 of u1, u2, but we can do it in general. That way we've done all local coordinates. Okay, so how do we make a tangent? First thing I have to make tangents. Well, if I differentiate x with respect to u1 at a point, that'll give me a tangent that's moving, okay, and along the u1 is this way. So it'll be a tangent like there. On the other hand, if I make differentiate with respect to u2 will give me a tangent there. So these it gives tangent vectors. So that gives two tangents to the surface. So far so good, so I'm consistent with how I start. And then I need a normal. Well, normal is done differently. Of course, how do we get a normal to a surface? We can take the cross product. So that's why I use the letter n. So the normal is partial x u1 cross partial x u2 and then normalized. Okay. So now I have tangents, two tangents and a normal. So I have my Gauss frame. Okay, now let's do second derivative. So I have the Gauss frame. So I have two tangents and a normal and the normal. So this is altogether, again, just the Gauss frame. Okay, so there's my coordinate system. So now let's take a second derivative and decompose it, just as before we took first derivative with respect to t, and we decomposed into tangent direction, normal direction, and binormal direction. So do the same thing. I'm going to take second derivatives, which is really just derivatives of the tangent, and decompose into all the directions. So let's do the computation. So it takes a little room. I'll start up high, and I'll go the first. So we take u, and then I'm going to take second derivative. So it's first that one? Let's think about it. Let's write down the left-hand side. So this is the equivalent of what we did before. That was derivatives of the tangent. Okay, now I have to take derivatives of the normal. And then I make equals. Okay, so let's think about it. The left-hand side is a vector, so the right-hand side has to be a vector, and it has to be linear combinations, okay, of the tangents and the normals. So it has to be a tangent, the other tangent, and the normal. Okay? So I write this all the way down. Now, I apologize for the length, but once you see the form, not only do you understand surfaces, you understand Riemannian geometry, because everything is in the Weingarten equations. Okay, so if you don't, maybe I would say, and if the level of understanding is only through the formulas, that's as good as me, because that's all I understand either. So, because how many people can picture 6-dimensional surfaces in 14-dimensional space? Impossible. So all we have is the formulas. That's why theoretical physics, after all the talk, there's no more physics. It's just formulas. Okay. Okay, now the normal vector, okay, let's think about it. It's the unit normal, right? So when I differentiate it with respect to u1 and with respect to u2, the right-hand side is 0. So the derivative of the unit normal it's perpendicular to the normal direction, so it only has components in the tangential direction. Okay. So here, look, nobody, and here, okay. So now the next step is put in the coefficients. Okay, well, the usual Gauss's notation was L. That's why I saved the letter L, M, N, and these two, no contribution at all. So now we know so far so good. Now how about these guys? Well, you can see that there should be some rule, but I'll write it out in detail just once, and then we'll see the rule. So there's coefficients here of gamma 1, 1, gamma 1, 1, 2. Why the 1, 1? Because it's two derivatives. Here it's u1, u1, so 1, 1. Okay? Here, no surprise, it's 1, 2, 1. 1, 2 because it's 1, 2. 1 because it hits the u sub 1. So now you see, so this has to be 2, 1, 2. And now we do 2. 2 because it's two derivatives u, 1, two derivatives 2, but it's because it's the u2 that we call the constant of proportionality, gamma sub 2, 2. And now you know I said we were going to write down the Weingarten equation, so this is the Weingarten equations. Okay, that's nice. What else can we see from the Weingarten equations? Well, we had a definition of the second fundamental form. So, oh, I didn't write down here. It's the alphas. Sorry, alpha 1, alpha 2, beta 1, beta 2. Alpha 1, alpha 2, beta 1, beta 2. Now there are formulas for the gammas in terms of the metric G, but let's not worry about that for now. Okay, it gets rather lengthy, and as I advertised the first time, okay, it's a long thing. You can get on math on the web. Type in Weingarten Equations in Google, and you'll get a whole list. Okay, but it's not worth remembering because it's a shorthand. Just as you can see, that everything has its own shorthand. So let's write down what's the left-hand side. Let's write this down. So shorthand. It's partial. Can we write this in shorthand notation? No geometry, just thinking. So what do you get the Ui, Uj? First of all, okay, how do I know Ui, Uj? It was the same, the gammas were the same. It's always, the gamma went with the Ij. So for each Ij, we can pick out the formula. Okay. The upstairs guy went which derivative? So if this is k, that's k. The left-hand guy was somebody times n. Okay? So for each ij, it would be h11 times n. In fact, okay? So I wrote the first three in one shot. Okay? Remembering repeated indices is summation. Okay. Now we see what happens if I take the dot product of the left-hand side with respect to n. Okay. For each ij, this is a vector. I dot it with a vector, so I get a, for each ij, I get a scalar. So this tells me it's hij n dotted with n, but n is a unit vector. So now I see I have the formula for hij. Okay. But what did we call the second fundamental form? This is just this guy dotted with n. Okay. And then the second fundamental form, I took this guy and then divided through by the determinant of the metric, and that gave me the second fundamental form. So here was the second fundamental form. So the h's are just the second fundamental form. It's the pi, but I have to make, so the h is, since it's dx dot n, okay, so pi times g, pi times the determinant of g equals these h's. And the h is Gauss's notation. So h was what? So there are three of them. So h11 was L, h12 was M, h22 was N. Let's erase here. I'm going for time? Okay. Plenty of time. So now, and what was the Gauss curvature? The Gauss curvature was the determinant of, the Gauss curvature was the determinant of the second fundamental form. And this determinant of the second fundamental form, in terms of the, okay, would be the determinant of H divided by G. But G is the determinant. G is the that means the determinant of the metric. If we have a surface, we know how to find distances. So this is the first fundamental form from the first fundamental. So now let's put it all together, and we get K in this notation equals determinant of G, but if we write G, you can write it as the, okay, as in the old-fashioned notation E, F, G, first fundamental form. So the determinant is EG minus F squared. So this is K EG minus F squared equals L, determinant of H, which is Ln minus n squared. Ln minus n squared. So you put a thing around that. Where is he? This was... Okay, so now we have Gauss's relation. Everything is Gauss. If Gauss invented the field, everything is named after Gauss. So what can I say? The Gauss formula. Okay. So it says from the second fundamental form, these LMN, when we did the decomposition, okay, we don't know them, but if we know the first fundamental form, we know EG and F, of course, but we also know K from the theorem of Egregium. So we know the left-hand side, hence we know the determinant of Ln and M. So they're not independent. So this is the Gauss relation. Okay, so now we have a few minutes. So there's two important things. First of all, can we answer the question that I motivated is there an equivalent for the Frenet-Serre formulas? Well, here were the formulas, Frenet-Serre for surfaces, but now called Weingarten, since Weingarten did it later. So Weingarten equations. At least something is not named after Gauss. Okay. So we have the Weingarten equations, which is just decomposition, second derivative, and decomposing into tangents and normals. Okay. And you could ask, okay, if this is the generalization of Frenet-Serre, if I give you initial conditions or some boundary conditions, okay, does this determine a surface? And for the Frenet-Serre, the answer was yes. For surfaces, the answer is no. And the answer is no for a very simple reason. So I can raise here. So I'll ask the question, and I already told you the answer. And as equations determine a surface. Well, those are the determining equations. Those from the point of view of PDE, are those the PDEs we should solve? And the answer is no. And why is it no? For a very simple reason. Okay? Because if I take, let's get some colored chalk. Okay. What happens if I take dd2 of this one? So that's second, and I take and dd1 of this one. You admit the left-hand sides are now equal? Right? The left-hand side, because this is two u1s and one u2, and this is one u2 and two u1s. So the left-hand sides are equal. So if I subtract, means that there's additional equations that have to be satisfied. And in the language of, so we have integrability conditions. We have integrability, consistency applied to integrability. Depends how you want to call it, or consistency. Conditions. Which gives you information when you do the subtraction. Okay, so if I do the integrability conditions, I take this one and subtract, and then I have to do the same for this one, dd2 of this one, and dd1 of that one. So I get two more equations, subtracting the second from the first and the third from the second. So I have two consistency equations. Well, what are they going to look like? Well, let's do it here. I don't want to erase everything because I need everything. Okay, so what are they going to look like? Okay, well, first of all, let's look at the first one. It'll look like the partial of L with respect to who? U2, right? Dotted with N. And then let's just work about the L one. That's enough problems. Plus L partial of N with respect to U1. So it's L. Okay. Then I have derivatives of the gammas, and then I have derivatives of the x's. But derivatives of the x's, I already go around in the circle. So if I hit this one, I differentiate with respect to u1, I'll have an x second partial with respect to u1, and x second partial with respect to u2. But again, then I can use these two formulas and substitute, get rid of that. Okay. So I'll have that. And then I have to subtract the other one. So then I have subtract off, and I have to take the second one with respect to U2, so it'll be partial of M with respect to U2 in the n direction, and then minus M, the partial of N with respect to U2. And then again, these derivatives. Okay. So it gets a little tedious. Okay. So right. Now we have to do the other one, and that says take this one. Which one are we going to do first? How about this one? So I take this one with respect to U1. That means take the partial of M with respect to U1, and then I'll be subtracting partial of N with respect to U2. So that's the partial of M with respect to U1, dotted with N, partial of N with respect to U2, dotted with N, and then all the rest. So it'll be the first one was M's I did, so it'll be M partial of n with respect to u1 and n with respect to minus partial of n with respect to u2 dotted n, and then all the rest. Okay, so first of all, there's only so many directions. So we have stuff not dotted with n, multiplying n. Okay. So we have stuff in the n direction. This is stuff in the n direction. And then I have L, say, partial of n with respect to u1, which is stuff in the tangent direction. So I either have stuff, when I balance this, I have stuff in the tangent directions and stuff in the normal directions. So the normals have to balance the normals, and the tangents have to balance the tangents. So everybody has to balance each other. So let's just look at the ones in the normals for a minute. Okay, I'm going to take my chances now, because, okay. So what do we see? So first of all, it looks like partial of L with respect to u2 minus m with respect to, this should have been 1, right? M with respect to, it should have been L with respect, which one did I do? L with respect to u2? So this should have been m with respect to u1? I never know. Okay, now I erase it, it's too late. So which one was the first one? This was correct, right? And this one looks wrong, because I differentiate with respect to u2. And then this one should have been m with respect to u1, right? Okay. And now this one has to be the first one was m. Here, this probably should have been u2. I don't know why. Should have been 2, because this one is 2. No. And this should have been 1. Partial of m with respect to u2, n with respect to u1, and equals stuff. So we have the integrability condition, so that balances the normals. So this balances in the normal direction, because these are. But then I also have to balance in the tangential direction. But if I balance in the tangential direction, I'll get stuff with derivatives of the gammas. Okay. If I take the stuff with the derivatives of the gammas and make the balance, I'll recover the Gauss's egregium equation. It'll be stuff about the derivatives of gammas. Gammas come from derivatives of G, and I'll recover the definition of the Gaussian curvature in terms of G. So balancing in the tangent direction will recover a formula for the Gauss curvature. In terms of G. Okay, so that's also true. So, okay, but I also know this has to hold either way. That was before doing any difference. Plus I have the Gauss equations. Okay, so now we're reaching the end of the day. So these are called, depending on, so those are called the Kodachi equations, and Kodachi did this roughly 1870 when I looked it up once. So it was about the time of Riemann and Gauss, and this is the Kodachi equations. So what does it say? It says a necessary condition to have a surface is the Kodachi equations have to be solved. So necessary. We've just seen necessary is Kodachi, and Gauss, which is very nice because this is what, let's count very slowly, not very hard. How many equations? 1, 2. 2 equations. How many unknowns? 1, 2, 3. 2 equations and 3 unknowns. Doesn't look so good. But we also have Gauss. 2 equations, you can get rid of one. Either you can take 3 equations and 3 unknowns, 2 PDEs, 1 algebraic, or if you like to eliminate 2 PDEs in terms of 2 unknowns, if you eliminate, say, M in terms of N and N. So we have, depending on how you like to do it, let's call it 2 PDEs and 2 unknowns. Okay. So necessary condition is in red. It says that the Gauss equations and Kodachi equations are necessary to have a surface. But the other direction is true too. So let's put it in blue. And a good place to start. But it's also sufficient. Gauss, if you can solve the Kodachi equations, solve the PDEs, solve the Kodachi equations under the condition of the Gauss equations, then it's also sufficient. And this theorem is called the fundamental theorem of surface theory. Just as a fundamental theorem of calculus, this is a fundamental theorem of surface theory, which says if you can solve the integrability conditions, satisfy the integrability conditions, there indeed is a surface. Okay. So I've done now 1, 2, 3, 4. So next time, higher order surfaces, okay, and the concept of curvature for higher order surfaces, and then what does this stuff have to do with mechanics and the connection with gas dynamics. Okay, so that's more or less, I think I can do that all on Thursday. Any questions from anybody? Yeah.
After we start Kodachi and Gauss equation.
What?
After we start Kodachi equation and Gauss equation.
Which is the Gauss?
After.
Yeah. Yeah. What is? Oh, there's 2 Kodachis. And the Gauss equation. These are the Gauss equations. The Gauss relation. No. That after you know, let's say no, Weingarten equation is after the fact. So, if you solve the Gauss equations, you know L, M, and N. Okay, then you have enough information to integrate up, because the Weingarten equations are now consistent. Otherwise, they may have been inconsistent if the cross partials didn't agree. Now they're consistent, so they're in the language of math, they're integrable. It's an integrable system, so we can then solve the integrable system for x and know the surface. So that's once you've satisfied the consistency equation, that's the proof of the fundamental theorem of surface theory. Once you've satisfied the necessary conditions, the system of PDEs that I wrote down, the Weingarten, which we erased, were integrable, and then you just can go back. You know L, M, and N, you can go back. In fact, it's almost okay. You know, here it is. You know the H, and now what do you have? You have an equation that some ddx of somebody, dx du, x dx du again. So it's a system of equations in the first derivatives equals known stuff. And you solve that system of equations. It's actually a linear system. At this point it's linear, and you can solve it. Then you know first derivatives, then you integrate one more to find x. But unfortunately, the Kodachi equations with the Gauss, Kodachi is linear, but Gauss is nonlinear. Okay.
For the case of the curve, you use the correct, your system will normalize all of them as a
For Nate frame, I guess that would.
Yeah, they're normalized. But in this case, you have.
I made the n normal, I think.
N is normalized, but the other.
I didn't normalize the tangents. It's not necessary. Any system of tangents, you will get the right equations. So, okay. And does it make any difference? I think
No.
always no. It's just a lower class average we can normalize that, but it's just like I always think these are the things that shouldn't make any difference because the surface doesn't know that whether the vectors were normal or normalized. The surface knows only about intrinsic stuff. So it only in the end depends on intrinsic information, which is to say the curvature.
Don't you have any consistency condition for the alpha?
No, the alphas don't. The alphas come in only to recover the formula for the Gauss, because they're in the tangent direction. So the tangent stuff balances itself, and you get there are formulas for the alphas, which I could write down. Everything's related. So again, I have it here. So it says the formula for alpha 1 is in terms of the second and first fundamental forms. I'll give you one just to show you what it looks like. Alpha 1 is HF minus LG. LG does not stand for the electronics company. And HF doesn't stand for Hewitt Packard with an F. Okay. So it's EG minus F squared. So this is the first fundamental form, and the EFG. So F and G were from the first fundamental form, and LMN. So this is second fundamental form. So there's some formulas for the alphas. So, but very uninteresting. Very uninteresting. So it doesn't add any new information. It just recovers in the end, the fact that the Gauss curvature is related to the second derivatives of G. So we'll get the true formula for the Gauss's, the general formula for the Gauss curvature in terms of the G, which we already know. Anything else? Okay, have a nice holiday, and I'll be back on Thursday.